control of.
No, but cursor I should see. No?
Cursor is not showing, sir.
Why?
We'll completely switch off. Something went wrong.
Why it is not doing? It was working.
Huh? This one connected?
That is on. No, but cursor is not seen.
Hello?
Hello.
Hello?
Anybody knows?
This light,
Sometimes,
who,
yeah.
who stop? lot of it.
and we have modeled this f of u is equal to u into 1 minus u, and he has shown the pictures yesterday. Okay. Just I will show you as a movie how it moves. This is the data, for example. This side is the water blue, this side is the red is an oil. This is the initial data. That is what u of x0 is equal to 1 if x is less than 0.5, otherwise it is 0, water level is 0 here. That is my initial data. Now when I started to solve the PDE with f of u is equal to u into 1 minus u, the numerical solutions you can see it. Okay, what is this? Open, I am doing it, but cursor I am properly see how to see it. Okay, yeah, I got it. Okay, fine. Next moving. Yeah, you can see it. You see that how the PDA as it goes, the water is coming down and oil is going up. Okay, at the steady state. Okay, how to go to the next page? Yeah, you want to go to the next page. It has came to. Okay, now. Okay. So now yesterday I was explaining how to construct a finite volume method. Okay. I think it is low or okay. It is also not coming fully there. It is for them it looks low or his height is fine. Okay, like a finite difference, I am taking the x axis as the division, for example, xi minus half, xi plus half, and so on. The length between this one is h. Yesterday I explained how discretization is done, and delta t, this is the time. So to get a finite volume method, I take this equation, this is equal to 0 del u by del t plus del f by del x, that is equal to 0. I integrate over in this rectangle. Okay. Then I will be having, since del u by del t is there and Tn to Tn plus 1, then I use the fundamental theorem of calculus. The first term del u by del t gives this equation here, and this one gives this answer. Okay, because del f by del x is there, again the integration with respect to x variable gives here. But at the point of xi plus half, the solution is discontinuous. Okay. So whether to give the left value or the right value. So then what a value should be given here. So to construct that, I will construct the Godunov scheme.
Sir, it will be Gmeet, I have to log in. 1 minute.
1 minute, yes, do it. Okay. Okay, fine, yeah, sure. Now I told that average value of how the finite volume method is an average over an interval. Therefore, if the average and it is multiple, that is the h and divided by h I am doing it. So 1 by h of this quantity is an average, that is uin plus 1 as I defined yesterday, and this is equal to uin plus 1 average of that multiplied by h, and this is an average multiplied by h. Here I am keeping Tn to Tn plus 1. So again, so what value I should put it here at the point xi plus half. Okay. Now for the time being, assume that m is the supremum of f prime of u. This is possible whenever the initial data is bounded. Okay, in the scalar conservation laws, the solution is also bounded by the same constant. Therefore, without loss of generality, if I assume that this m is finite quantity, then I am so now I am going to the Riemann problem. ut of f of ux is equal to 0, u of x0 is equal to ul and ur. Yesterday I gave some how to construct the Riemann problem for a convex functions. So let me call it, this is the split at x is equal to 0. So the Riemann problem solution is given by of the form x by t, ul and ur. Okay. Such a thing at x is equal to 0, one can show that it is a continuous function. So therefore, this can be written as f of that, once it is a continuous function over the grid. So then what happens is that this side f of u, the x is a constant, the vertical line, therefore the speed is 0, that means slope is infinity, therefore f of u minus f of 0 minus is equal to f of 0 plus by the Rankine-Huygens condition. That is why we can say that it is a continuous function. Therefore I can say that these values are equal, this minus 0 minus and 0 plus are equal. Now I am coming to the Goodenough scheme. So I want to find f of u of xi plus half where the solution is discontinuous. So what Goodenough does that, this is an important basic thing. For example, t equals Tn, you know the data here, and you want to compute a solution of the t is equal to n plus 1. So now, as I said, xi minus half to xi plus half, the middle point I will call it xi, that is why this he uses these notations. The midpoint is xi. So the left side is vi, right side is vi plus 1. Okay. Now in the way he constructs in such a way that the wave starting from here should not cross xi. So delta t is so small that delta t into this distance is h by 2, speed is maximum of f prime of u, the coefficient of ux I told that is we call it as a speed, maximum of f dash of u into delta t should not cross, that is the length of the wave should not cross, that means it is h by 2. Okay. If this happens, the wave starts from here and this side, they do not cross xi plus 1, they remain such a way that first you construct that. Delta t is chosen so small that, okay, the waves from starting from the point xi plus half should not cross this xi plus 1 this side and xi this side. So they do not, the waves from this one, they do not hit each other, they are separately as there. In this case, he puts the solution as the, now the Riemann problem solution, because in sub 0 it starts at xi plus half, the solution is given by x minus xi plus half. If x is equal to 0, xi plus half is there, then x by t will come. So now this is the solution of a Riemann problem. Okay. And he gives, this is the value of the Riemann problem, that is at the n plus 1th level explicitly. This can be given by the Riemann problem solution, left side is vi, right side is vi plus 1. For that value, so now I am coming back to the scheme, then here we will put that value 0 minus and 0 plus position, the Riemann problem of the solution at xi plus half, that becomes 0 minus 0 plus, that is why he puts here, and he rewrites the scheme as the, now the flux value at the flux of u at the point xi plus half is nothing but this one, this is nothing but this one, that is what he call it, this is the flux, it is depending upon two variable, he constructed 3-point schemes. Now this is the, if you look at this one straight away, it is bit complicated. That means you have to first solve the Riemann problem and put inside the f. For every time you have to solve the Riemann problem, but to avoid it, but he was very cleverly, without computing a Riemann problem solution, without this value is exactly he finds it. Okay? U is less than or equal to v, then it is a minimum of f of this one. This is the formula is given by him. So it is a beautiful formula given by him. See here we are not solving the Riemann problem, but still you can have this one. So when he gave this formula in his thesis in 1954, he sent to the journal, but no journal accepted to publish it, because they said that there is no mathematics journal said there is no mathematics in it. He guessed that what is the formula. okay, by experience, and he guessed it. And somebody says, okay, why don't you send it to physics? They said that there is no physics in it. There's even if it's trivial, he couldn't publish it. So in 1959, his Petrovsky, he was an editorial in the board of the Mass-Bornik. So he saw that, and with his influence, he was able to publish that paper in Mass-Bornik. But now today, it is the one paper highestly quoted. Any conservation law numerical method, without that reference, nothing will be there. Okay? That is one of the fundamental scheme, and it is among all the first order scheme, it is the best scheme. No scheme can beat it among the first order scheme, because he solves directly the Riemann problem and guesses the formula and he gives it. So what is the importance of that? If f is an increasing function, we can see that it takes the backward difference, f of u, f of uv numerical flux, it takes this value backward and forward. If f is decreasing, it takes the second value, and if it is a non-monotone, exactly what is supposed to take, it takes it. That is the beauty of the scheme. So if it is, but here the main difficulty is that minimization, the maximization problem. But in the case of a convex function, we know that it has the only one minima. In a convex function, global minima is nothing but global minima is the only one. So you take that, a theta f is the minimum of f of u, then you can give the formula can be reduced in this fashion. Okay? Now it is an explicit for a convex function like Burger's equations or many other equations. So it handles, the formula becomes very simple. If f is monotone or f is convex, if f is concave, all maximas are replaced by the minimas. That is all in the change in the formula. So now the question was in 1980s, engineers wanted, okay, we don't want to check your convergence analysis, proof and so on. We want one theorem, okay, we just check what is it guarantees that it should converge to an entropy solution, because I told that weak solutions are not unique. So mathematicians were searching for a result, one theorem they wanted, just they will check the condition of a theorem. They don't want to study other parts. What is that condition? So that as soon as the scheme is satisfied, that condition is satisfied, automatically uniqueness, existence, everything should be over. So in the around 80s, 90s, Crandall and Maida, they were able to come up with a scheme. Suppose you call this, the scheme is consistent and conservative. Suppose if it is a 3-point scheme, Vi minus 1, Vi, Vi plus 1, if h is increasing in each variable, if h is increasing in each variable, then you need not to take it off, automatically it goes to the, you need not to check, it is a round off error, whatever it may be there, it will take care of by itself, and it is a high stable schemes, it converges to an entropy solution. In the first, but unfortunately what really happened was, if any scheme satisfies, this is called the monotone schemes, if h is increasing in each variable, then it converges to an entropy solutions, no doubt about it. Unfortunately, this scheme is at most first order accuracy, okay. You cannot have a better accuracy. At most first order accuracy, in the two-dimensional thing, if you want to have a better accuracy, then you have to put number of points, and that becomes a computational expensive. That becomes a computational expensive, but we have to go to the higher order. Even for a linear problem, one of the main difficulty in proving this result is that we cannot have a L2 stability is not enough, because L2 stability, for example, Lax-Petty scheme, we have L2 stability. Yesterday Dubé has told that it has an oscillations, okay. He showed in a graph it has an oscillations, that doesn't converge. But truly L infinity stable scheme, I wanted it, solution should be bounded. If the initial data is bounded, solution is bounded theoretically. So we have to develop a scheme, higher order scheme, so that u naught is L infinity, that is a bounded measurable function. Then I wanted that u of xt should be also in L infinity, okay. But even for a linear problem, ut plus ux is equal to 0, you cannot have. second order scheme with both the conditions. Only L2 stability you can have, but solution oscillates there. On the L2 norm, it goes to the solution by the Lax equivalence theorem, but in the nonlinear problem, it is not possible. You cannot have even a second order scheme fully, globally second order scheme, or you cannot use the central difference scheme, second order schemes. So what they did was in 1976, Van Leer, he is a aeronautical engineer, but they need the results, in the aeronautics conservation laws plays a very important role. So what he did was, the idea he bought it, okay, you take a Lax-Van scheme, where you will oscillates, there you locally reduces to the first order. Okay? Locally as a monotone scheme, where it oscillates, your scheme recognizes oscillation as soon as comes, it reduces to the first order. So globally it is not a second order, but locally it can be a second order. So that idea gives the wonderful results. After that, he constructs the total variation diminishing schemes. After that, people started to work on all that kind of higher order schemes. That was the basic scheme was developed by the Van Leer. Okay? In 1976, he has written 3 or 4 papers. They are very important. Those who want to study, that is the original things. So in you can see that Journal of Computational Physics. All those papers are appeared in Journal of Computational Physics. Okay? Nowadays, they call it as muzzle schemes. MUSCL. The word is coined by Van Leer, that muzzle, the word. Monotone, upstream something. Central schemes for conservation laws. Yeah. So once it is a monotone scheme, then L-infinity stability is valid. Okay? And one can show that it converges to the another. Is there any other scheme other than Godunov scheme? Because it needs the minimization, the maximization. So can we reduce the computational work? Then Inkster and Osher, they came, instead of minimization and the maximization, we can use the integral. Integral is comparatively simpler than the minimization and the maximization. Okay? They came with this one. This is also an upwind scheme, but unfortunately, in some cases, Godunov scheme is better than this one. Okay? This is another scheme proposed by the Inkster and Osher. Now the question is that, is there exists a non-upwind scheme? Okay, till now I told that when the wave is moving from left to the right, backward, otherwise it is a forward. So is there exists a scheme without upwind? So there is a old scheme before this Godunov idea. It is proposed by the Lax-Friedrich. This is one of the Lax-Friedrich scheme. Okay, yesterday I think he has done, Dubey has mentioned about this one and how to use the pin for this neural network and so on. This is also another scheme. Okay, Lax-Van scheme is not that one. So it's oscillated, it's not a monotone scheme. And the question is again, I told that the convergence analysis, even you have a second order scheme, it is not monotone scheme. Okay, that theory has failed. If the scheme is monotone, it automatically go to the entropy solutions. When the scheme is not monotone, when you go to the second order schemes, because the monotone schemes are at most first order accuracy. These schemes in general, if it is a second order or third order, total variation diminishing. What it means is the total variation is diminishing means, I tell you. Total variation means, suppose your solution, suppose your solution is like here, okay? This amplitude, sum of the plus this height, sum of all these heights, amplitudes. If they are finite, then we say that the function is of bounded variation, okay? All the amplitudes. So now the question is that, theoretically we know that as the time increases, the maxima decreases and minima increases, total variation becomes smaller and smaller. Okay? This happens in the case of a theoretically one can prove it. But numerically, how to establish these conditions? So 1960, Lax and Van Drop proved the convergence analysis, convergence theorem. People took 20 years, okay, when what is the condition we should put it. If they want one theorem, okay, can you state a one theorem? As soon as the condition is satisfied, it should this total variation as the time increases, it should decrease. Okay. And around 1982, Horton came out with a simple idea. Okay. He proves that total variation TV of Vn plus 1 is the total variation sum of the amplitude at the n plus 1th level. It should be less than or equal to sum of the amplitude of the nth level. This is the condition. This is possible. He states the following theorem. This is Horton's lemma. Okay. This is very simple proof. He gives that few lines, the proof will be over. But people took long time to understand that one. What he did was, any scheme Vin plus 1, write Vin Ci minus half del V minus half di plus half. So when the wave is moving, forward difference some places you take, some places take the backward differences. So this represents the splitting the scheme as forward difference and the backward differences. Ci minus half represents the backward difference, di plus half represents the forward. He splits it correctly and he puts this condition. Okay. He was able to write it, and this is the proof, simple proof, it's a few lines. So you can see my notes, I have mentioned it. So if this condition, Horton says that Ci minus half is positive, di plus half is positive, sum is less than or equal to 1. What is that sum? Yesterday Dubey was telling that coefficient of viscosity. The sum is nothing but the coefficient of viscosity. Okay. So when the scheme is better, means you have to reduce the coefficient of viscosity smaller and smaller, so that you will get a better answers. Okay. But how much you can go to small? How much you can go to small? You cannot take it 0. If you take it 0, it's a central difference, immediately unconditionally unstable. No, everywhere it's unconditional. What should be the condition should be given. Okay. Next theorem, I think. Okay, this is the proof of that one. I think I didn't mention. Okay. The condition I will tell you, the coefficient of viscosity cannot be 0, but it has a lower bound, that is nothing but the speed of the discontinuity. This is the f of Vi plus 1 minus f of Vin divided by Vi plus 1 minus Vin modulus of this one lambda should be less than or equal to Ci plus half n plus di plus half. This should be the bound of this is nothing but the coefficient of numerical viscosity Q. So this should be above than this one. It cannot be less than this. That is the speed of the discontinuity. Your x dash t. You know that f of ui plus 1 minus f of uin is nothing but x dash t ui plus 1 by uin by Rankine-Huygens condition. The speed of the discontinuity should be below the lower bound for the coefficient of viscosity, then only the scheme is total variation bound. Then in that case, why don't you take this itself as the coefficient of viscosity, because it is the least one, but unfortunately if you take that, it does not converge just to an entropy solution. It is a weak solution, but does not converge just to an entropy solution. Therefore, among all the schemes, the lower bound is achieved by the Godunov scheme. That is why the best scheme, you cannot improve further the Godunov scheme. That sits as a more or less talking to the entropy solution, it sits as the best in the beginning. So this is what, so I give you some example, numerical example. It is numerical example is done by long back by one of my collaborator, and he was working for his PhD. We were working together. Sudarshan, now he is a faculty in the ISER Trivandrum. So he gives some computational work of the second order schemes by using the idea of the Van Leer, as I mentioned. So that is the just I will give some these solutions, since it is a monotone schemes, they go to the Khrushchev satisfies the entropy condition and it goes to the entropy solution. The proof, mathematical proof will be over. And this one I will give just by the oil industry problem. Suppose this is an oil bed, it is blocked, okay. It is an oil, either the oil is here, then what they do is that this is an input well with a high force, they pump the water inside, since water started to push the oil towards this output well, and they pump out it, okay. This is the basic idea of the oil industry problem. So this is called usually in the literature quarter of a 5-spot problem. They don't put one pipe or two pipes, there will be many pipes, because in my here in the picture it is a square of 0101, but it is there in practically it is in miles. So what they do is here, look at here, okay. This the, for example, this the water with a pipe, they send it here with a high pressure, then water goes this side, this side, this side, this side. See, water from here, it goes this side, this side, this side, this side. So it's a 4, it covers the 4 squares. So then when you go to this side, it pushes the, this is a sink where it goes there, and they will pump out at it here like that. So it is the 5 point, 1, 2, 3, 4, 5, 5 points. Quarter of that is that where I am studying, but symmetrically I can study other places. That is why it is a quarter of a 5-spot problem. So there is a Buckley-Leverett equation that gives that how the flow will be going when the water is pushing the oil, how that flow is explained by this Buckley-Leverett equations. It is around 1930s it was derived, modeled. So here you look at the things, when it is a water is pushing, there will be many kinds of rocks, okay. There are hard rocks, the permeability is 0, and some sand rocks, there is some permeability allows to enter, and like that. So in the spot, the permeability of the water and the oil, in the formula it will come as a mu L, and the medium may be heterogeneous. Suddenly rock comes, different kinds of rocks will come, okay. So therefore medium becomes the heterogeneous, it may happen. That is why this K represents the heterogeneous media, it depends upon the Kx. This is called an absolute permeability, that means it is nothing to do with the solution, it is depending upon the ground, field, okay. It explains the field where it depends upon x variable. So where the field is heterogeneous, okay, but it is discontinuous, suddenly there may be a change in the permeability. Here left side is very good, right side may hard rock come, and this side may be change, okay. So here this the mu L is the water, this is the viscosity of the water, mu L viscosity of the oil, okay. So now we do the experiments. I am not going to just showing as a pictures how numeric. This is an example. See, the pushes the water, complete blue color shows that complete water is occupied. Here some yellow means it is not purely water is there, mixture of the oil and water is there. So what happens with a high pressure, if you push it, with a high pressure you push it, then water moves towards this diagonal, because it goes with high pressure in the same direction it moves. Then what happens, more than 70% of the oil is left, because once the water moves this output, no oil can enter this, because oil cannot push the water. So it is a complete failure of the most of the petroleum industries, they will be in a loss only if you send it by water. What they did is that I wanted to move water slowly, even though with high pressure. So what I should do, I have to thicken the water, okay. That means I have to increase the viscosity of the water. Viscosity means how much retardation to flow. Slowly it should not move rush, it should not with a rush. So as I told you, I showed mu L viscosity of the water. Now we will dissolve some polymers, the concentration of the polymer in the water, that I will choose that mu L I wrote now. Then we will make is that viscosity of the water is not fixed, mu L is depending upon the concentration of the polymer. So I am increasing, mu L is an increasing function of the concentration. Now if I do these experiments, then mathematical problem becomes a bit complicated. This I also just I will show the, hope this video will work. without dissolving polymer. Yeah, see that the water is pushing, but water once it reaches the output well, nothing can be done. Okay. How to change the page? I have some again. Can you help me? Next page I wanted to go. Okay, fine. So be here. Huh? So now we add the concentration to the water. Now in some scalar law, this becomes a systems of equations. Okay, concentration, solution is depending upon now concentration. Okay. So now it is a system of equations. Now once you solve this one, okay, this now I will do the experiment. First I will start with a more or less a homogeneous media, not such a heterogeneous media. So this well and water started to enter from here. I start in the first cell, already water is there. I zoom it, I take it, and next I will show the rocks here, different rocks. So what you do is that while doing computation, you find small circles. Small circles, you will have put that in that circle, permeability, what you want, less or more or like that. So if you put permeability is equal to 0, that shows the rock, hard rock. It does not allow any water or oil, because water has to go around of it. If there is a sand or something, some rocks may allow it permeability, then you give 0.2, 0.3 according to your choice. So how we are doing the computational thing? While doing computational, how artificially we create some rocks. Okay. So now you can see that it is almost more or less it are the sand rocks. This is a good media, it is not heterogeneous. So you can see it now. See, this is with the after putting a polymer, water is thickened, it moves very slowly. See, it's already it has reached towards the output, but if the water becomes thick, then it started to move slowly and it sweeps better. This shows. Even though it moves slowly, but it sweeps better, it is not leaving an oil. So now if suppose the heterogeneous media, this also video is there, you can see it. Yeah, left side without polymer, right side is with polymer. Left side goes very slowly, but it sweeps better. It is not leaving. Of course, practically we have some more difficulties, practical implementation, but it is some kind of our numerical experiments, it is an ideal experiments. Okay, practically we may be having some other difficulties. Fine. So this is with adding the gravity. If you don't want to send it to this side, by applying the gravity, then it comes towards the bottom. And next example gives the hard rocks. These are all that red color I told you how to produce a hard rock. On the domain you put a small circle, give the value of a permeability something like 10 to the power of -5. It is almost 0. Okay. So then it reacts as a hard rock, values there. Then you can see that, see here left side without a polymer, right side you look at it, since they are the hard rock it cannot pass through it, so it go around of the hard rocks. So you can see the same, this is the same numerical thing. Yeah, you can see it now. There is some other graphs by mistake I put it. It looks like a homogeneous thing. I think I put the previous picture Yesterday while copying, I think I have done a mistake. It is not the graph, but however, this is the one with the rocks. Right hand side it's cleanly sweeping, it goes around the rock. There it is moving very fast. The water has the viscosity is very less, that's why it is moving very fast and moving towards the well and leaves the more amount of oil inside. But here look that it is not leaving the oil, trying to cover it. Let me see this video, you will see it may be better. It is coming. You see that right and the left side without polymer, right side is moving very slowly, but it goes around the rock and cleanly takes. Of course, this is not just, it is just a practically we have other difficulties. Rock has holes. It is not just I did it numerical experiment, it is very ideal experiment. Practically what really happens, the rocks have holes, oil goes and enters inside of that. Okay. Some breakages will be there and oil goes, enters that, and picking up, how to pick it up. Water don't go, water goes straight away. It won't go the depth and picking that. Because they are so small, the rocks, this thing, water cannot enter, oil already, because oil was before than the water. Oil was there before in the holes of the small holes of the rocks, and water only rushes, but it won't take those oils. There is a next in your theorems, in your practicality, you have to add extra conditions now, like this. First you do it a very simple example, then slowly one by one adding the difficulties. Okay, that is how the research goes. One paper, this, one paper, adding that, you know. So this completes. Is actually one can see that this more explanation is given in this paper is also appeared in Journal of Computational Physics in 2014. I think I will stop my lecture. Okay. So some motivation to give. Of course, practical problems much more difficult than I explained. But how our numerical schemes works, how good is efficient, that is what we wanted to share. Okay, thank you. This gives us some motivation to how the practically the problems comes in the industry.
Hello. So thank you so much, sir. Participants, any questions? So sir is giving a lecture from yesterday. I hope you have some questions. Any questions? Okay, there is no questions, then, so thanks again. So once again from our side, the Professor Vidappa Gowda sir, and also we want to facilitate to give some honorarium. So calling to Professor Novin sir to come here. Thank you, sir. So now we are going to take for 15 minutes a tea break. Then after break, we will start the next session. No. Otherwise, anyone can join and talk.
Okay.
Anyone can join outside
Okay.
in your mobile and talk. Is it?
Oh.
Or join and talk.
He's speaking just hello.
Hello. Speak.
சவுண்டா பேசு. வேற ஏதாவது பேசு. வெறும் ஹலோ சொல்ல வேணாம்.
No. No, it is not connected properly. Or something on or off there.
It's connected, sir. ஒன்று கீழே ஏதோ ஃபால்ட் பார்த்தேன் சார். இதுதான் சொன்னோம் ஃபோன் பண்ணுறது.
Good morning. Good morning, Professor Pravir Burman with us. We are going to start that session, but before that, okay, sir, we are checking audio things, then we will start it. Sir, just we are checking some audio issues is here. Okay. So after that one, so I will inform to you. We will start it just for a few minutes. Where they went always?
Just waiting for this. These have some issues on ground floor.
audio.
இங்க ஸ்பீக்கர்ல கேட்க மாட்டேங்குது.
Hello, sir, can you hear me? Just 1 minute. Hello? Unmute first. with us Dr. Probir Burman, Assistant Professor from ABP, so Triple ITM Gwalior. So I am going to, it is my great pleasure to introduce him. Let me introduce for a few minutes for all of you. Dr. Probir Burman is an assistant professor at ABP, so Triple ITM Gwalior, specializing in numerical heat transfer and scientific computing. He earned his PhD from IIT Dhanbad, previously ISM, and subsequently completed a postdoctoral fellowship at IIT Kanpur. Prior to joining ABP Triple ITM Gwalior, he served as an ad hoc faculty member at NIT Warangal, where he gained valuable teaching and research experiences. Dr. Burman's research background lies in the numerical modeling of convective heat transfer and fluid flow using classical computational techniques. More recently, his academic interests have expanded towards physical informed machine learning, particularly the theoretical foundation of PINNS and its application in CFD. His workshop lectures focuses on the formulation of PINNS, their underlying mathematical principles, and their relationships to traditional numerical methods for solving partial differential equations, with an emphasis on strengths, limitation, and open challenges. Please, Dr. Probir Burman, sir, please continue. You unmute, sir, please, unmute.
Okay, thank you for introducing me, and thank you to the organizing committee for inviting me in this workshop. So, am I audible?
You are audible.
And can you see the slides? Is it
okay.
is it moving? No? It is. The changes it is showing now. I'm changing one to.
Yes, everything's fine.
Okay, thank you. So, good morning to all of you. I'm Dr. Probir Burman, and today in this talk I will be talking about not any research work which actually been done using this physics informed neural network, but I will try to talk about the basic framework of pins. Correct. So, and followed by hands-on after this. And sorry, sir, how much time do I have? It is 10:46.
You
Okay,
have actually two lectures, sir. One is theory, another is practical. Two consecutively we kept, it will go up to 12:45. In between you may take break, sir.
Okay. Thank you. Okay, so in this talk, actually, I will actually talk about why, what is pins and why do we use it, what is its core idea, is it actually linked with this universal approximation theorem or UAT, then this differentiating this network which is essential to find these losses that we will see, then how can we design the loss functions, then the training strategy and some case studies, and some more we will see in details with hands-on and some common pitfalls. Correct. So let's start, and in between if you have any queries you can just stop and ask me. So let's start with what is pins. So pins, actually it is abbreviated for physics informed neural network or physics inspired neural network sometimes. So actually here we have it is actually using pins we do approximate a solution for a partial differential equation or ordinary differential or maybe system of. Okay. So here actually this gamma actually it contains all the parameters which actually in terms of weights and biases. So if we have an PD in a domain with some boundary conditions on its boundary, so here actually we will try to fit a neural network U gamma x which should satisfy this PD along with these boundary conditions. But this these pins can be used for forward problems, which are actually we are solving the problem, and for inverse problem also. So here we identify the parameters or coefficients from the data to for a PD and also for data assimilations. So actually, if we see this physics and data paradigm, this spectrum, so here here the physics actually we refer to the governing equations. Those are actually maybe coming from mostly coming from this conservation of loss and this or balancing those actually we actually define. So this physics here we refer the governing equations, and data we may have a problem where we only know the governing equations only, like and we don't have any data, and or we have small data. Here small data we do refer that we only know, let's say, only one boundary, or at initial point we know some data, but remaining we know only physics. We may have some amount of data and some amount of physics, and we may have a huge amount of data, but physics we don't know. So here actually this physics informed neural network, that actually where we have small data and lot of physics, right? So and in this when we have big amount of data and we have small amount of physics, we can those actually we can go for this it is called some sort of this inverse problems and this type of, and this some amount of data, those actually falls in those cases. Okay, so let's so before starting its formulation for pins, so this is one very popular theorem. This is actually in machine learning books they write UAT, universal approximation theorem. So informally if we say that any continuous function that can be approximated with respect to this that means if we want to say a neural network with one single hidden layer with arbitrary number of perceptrons can approximate any continuous function with arbitrary accuracy. Correct. So that this actually gives the guarantee that this neural network will actually approximate the function at least. So, but when we try to fit it for our governing PDs and ODs, actually this is very hard sometimes. Correct. It actually depends on many factors like geometry, the type of PD, if it is convective dominated. So in that case, it becomes very difficult to have a solution with good accuracy using pins, and also time also are very crucial, the computational time. So actually this gamma, actually it is the set of all W and B. So here actually we try to optimize to find best possible this weight and bias vector so that it is it approximates that function. So in pins, if we see it's means steps, we can find that now we can see that here actually it is very simple. Here you have to define a fit forward neural network, then you have to and the domain of computation where you have to generate the random points or this collocation point, and also on the boundary also, then you compute the residuals, and you take here in this case we take the discrete 2 norm, and we try to minimize for gamma. Actually this gamma as I have told, those are and we compute the arc mean on gamma, and the total loss, actually we do optimize this, and we will see subsequently. So here if we see, we have these steps mainly. If we see from the first, if you are starting from the first time these pins, although nowadays there are so much advancement that are made in this field. So here and we combine all loss functions. So at least up to this, you can start with that loss function from the interior domain and loss function from the boundary, and this is a hyperparameter which actually we fit that how much weightage we want to give to the boundary loss or to the PD loss, right? So sometimes actually this dominates so much, this PD loss, that the network don't try to learn this, actually satisfy this boundary condition, rather it only optimizes this interior loss. And this is if it is with you, you have some noisy data misfit, and it is mostly required for common for these inverse problems. Correct. So for forward problem, actually you can start with loss with this PD loss and with boundary loss. Actually here boundary loss refers maybe initial condition or boundary condition, both we can take care. So here is a very common architecture. So we have this, this is input layer. So in input layer we have only spatial coordinates from interior and boundary. Then we have these hidden layers. Here actually this sigma we refer to activation function. So we'll talk about activation function, which type of activation function we should take, and there are some restrictions in terms of pins. Then we have those approximated these outputs. Those are actually, we can say, solutions, and then we compute these derivatives for this network, and we compute the residuals, and from boundary residual or also this initial condition residuals, and in total we have our loss function. This is the loss function. If we add up this internal and boundary, then this loss function we do optimize and we find gamma star. And if let's say it is gamma star, if it is, you are not reached up to that desired level of accuracy, then again you update weights and bias here, and again you compute all of this and again optimize it. Like that, this loop will this iteratively we will keep on going. Correct. So and then if you want to see that how we can compute this loss functions. So for interior point, those are number of interior point in omega, and we will sum up. This is this we can compute with discrete 2 norm. Actually this norm is discrete 2 norm, and for boundary also, taking some boundary points on the along the boundaries, and also if you are have some sensor data or means observed data, that loss also we can incorporate with these pins. And this actually, and also we have to take care about those hyperparameters, that we have to do this tuning for how much weightage we want to give here for this data, how much for PD. Those we actually take care mostly by observing till now, what as per my knowledge. And we try to reach to our desired accuracy, but there are some pitfalls. Not always you for all problem you can go up to your desired accuracy, right? So those are some what is called common choices we make to generate random points inside the domain. So we use this Latin hypercube or this low dispersion, this Sobol sequence. It is pseudo what is called a random point, the Sobol sequence that can make. And also you can use these mesh-based grid points, which actually if you are working in CFD or FEM, from the mesh grid nodes also you can import here and just use it. And also this type of problem which actually we do encounter in this in terms of these numerical methods also, where a boundary layer appears and those things, because of this gradient become very stiff. And this is we also go for adaptive sampling. So there, wherever we have the error is very high, let's say this is the domain of computation, correct? So only this part we are hitting. So here actually, or in this corner there, the physics is changing very rapidly. So in that case, we can for efficiency, if we increase the number of nodal point in the whole domain, so actually our computational cost it increased very rapidly. So rather we go for where we have disturbances. The physics we are unable to capture with this sparse data nodes, nodal point. We actually try to add more points and compute there. And also you can see for this those papers that like XPin, which actually if you refer, it has the idea of this domain decomposition, which is maybe known from this FEM or this numerical methods, or this residual based refinement actually. That is also you can see those are you need just have to refine your existing code if you are using let's say some PyTorch or TensorFlow, where actually you have to compute for this case the error, and you can increase the number of nodal point, means close to that nodal point. And for XPin, there is a research paper, and also in YouTube, Professor Amiya have his videos. You can go through very nicely. He have explained those things. So here, actually, we are very familiar with this in Python, this NumPy array and those data structure. But for pins, for deep learning, actually, this NumPy array it may not be sufficient for this. What is called or maybe sufficient to write the code with without having any what is called means you will have difficulties, because in this case we have to compute these gradients, and also we seek for this GPU computation, because the computational time is very high, and also computing this actually also higher order derivatives, and also this optimizer. Here actually we are dealing with millions and billions of parameters. So this in pins, actually you may have, if you have difficult type of problem, and based on geometry, the number of the computational time may be very high, and these optimizers also need to work like Adam, then LVFGS. So we actually this tensor, this data structure, you should go through in details if, about this tensor data structure if you are not introduced. And also this mini batching. So those are actually you can see those techniques when in a, for introductory deep learning courses also. So actually here actually we have this differentiation that actually we do take care using mostly this autograd or computing the Hessian or this Jacobian. We will see in our this hands-on session. So, so there are some in side-by-side comparison. If we say that why we should shift to this tensor rather than this NumPy array. So actually, in using tensor, yeah, it will be very hassle-free to write the code. You have to write very minimal number of lines of code, and you can solve your problem. And mainly, actually, this feature, autograd feature, actually, it personally I do means like this, which I found most means important part of this tensor rather than ND array, because in this case, ultimately the loss function will come in terms of our these derivatives, correct? So here actually one example, through an example we can see that we are solving this Poisson problem, and for this we will compute this residual, correct? So as we have told, but here we have to compute this second derivative, and we have some this right hand side function. So in this case, actually, we are actually dealing with the steady equation, so this time derivative is not coming in picture. So here also for the boundary node, you define the boundary nodes and you compute the residual. So let's say the boundary, it is not defined here. Let's say it is gx. So ux minus gx also should be less than given precision here. So actually, in pins, this satisfying this Dirichlet boundary conditions exactly in this way, it is actually way hard. Actually, here we are actually computing this L2 norm. It gives the sense of how much overall loss. But in 2-dimensional, 3-dimensional problem, sometimes let's say the cursor, if you see that this boundary is 0, if you see, yeah, after training, it may have this type of oscillations. So actually, overall, actually, it is giving up to, let's say, 10 to the power minus 4, but it is not exactly like many numerical method. We do impose the Dirichlet boundary condition in force that way, but in pins also, it is not possible for all cases. In many cases, we actually take care of the initial condition by defining the neural network in such a way that means the network itself will be 0 at 0 or given initial condition, or maybe boundary condition. If possible, you can design the neural network in such a way that you actually no longer actually depend on this residual on the boundaries. So in this case, the boundary condition become actually for this PD. Some actually what we can first think of that some PD, it should at least the approximate solution should at least satisfy the boundary conditions that should be there. The at least the Dirichlet condition should be satisfied. But computing this loss sometime that not become sufficient. But this way it is also not possible for all the cases. If it is possible, then it is very fine. Very we should go with. And for training, we use this Adam. It is actually it works very efficiently. And it actually it works slowly, but it means it is if you have noisy gradient also, it is it works very robustly. But you can try with this LVFGS. It is based on this it is a pseudo Newtonian method. So here actually you can see that it has means it will have two loops. One is interior means loop, and it will have exterior loop. So it will make some batching, and you can see that it will it is way more faster than this LVFGS. But sometime if we directly start with LVFGS, actually it may fail, and it may show that NaN in case you are using this PyTorch not a number. This type of error you may get. That's why you can give a smooth start with LVFGS when your network is maybe some 100 or 1000 epoch if you go through, and then if you start using LVFGS, that may work smoothly. That's why this hybrid strategy also nowadays it is using, because LVFGS will work. If it works, it will work very means efficiently. Within few epoch, you can see that your problem is solved. And also this learning rate scheduling you can go with, and this because because in pins, if you see that mostly if you just without using some type of this X pin or some taking care some special take care, if you just go through this architecture, so most of your research problem you will see that the this loss, it will actually keep on fluctuating in a plateau of 10 to the of order 10 to the power minus 4, maybe 10 to the power minus 4 3. It will keeps on oscillating, correct? So this type of issue actually we do we do encounter. And one other important thing for this activation function. So here actually if you are dealing with a second order PD or higher order PD, the activation function should also be means should be at least differentiable of that order, because if when we are actually differentiating this this network, if when we are calculating a derivative, if we think of you have only let's say you have only one, so without loss of generality, let's say this alpha j is equal to 1. You have a network only one neuron, that is or this one perceptron, and let's say you are approximating this gx with this, and this gx is this function you are approximating a Laplace equation. So to approximate it, what you will do, you will calculate g double dash x, and you will put it to the PD. Okay, you will put it to the PD and compute the residual. So ultimately, when we are computing the derivative, what we are doing actually, it is we use the help of this back propagation. That is nothing but in this case the chain rule derivative. So it is a function of so let's say you have an activation function here. So it is a function of this x bj. So first you will derivative this inside this function, then you will take the derivative of this function, then you will have the total derivative, the complete derivative, and again you will differentiate it twice. So if you have multiple layer, it will be again a function of this activation function. So actually here we can define this actually neural network. It is the combination of an affine transformation followed by a nonlinear activation function. Okay, so that's why we do take the activation function, which should be continuously differentiable, like tan hyperbolic or this sigmoid, but not those activation function which don't have which is continuous but not differentiable. That we should keep in mind when we are actually dealing with pins. Then actually to have good stability, we should take about this normalization, then scaling inputs outputs, and also this tuning these hyperparameters like this those okay, this lambda b lambda d, those hyperparameters, and also this we should keep on monitoring this at least the boundary conditions when actually in the applied when you are actually using for some, let's say, solid or fluid or some other domain, you are actually utilizing pins. This how the network is actually what happened here. Sometime it actually take care of the network only boundary or maybe only PD it is taking care, and the other part it is not taking care. So in that case the results are you will see this that will actually deviate from your numerical result or the analytical result if it is known to you. So this thing actually while training we do take care, but till now, as if we say for this only solving these PDs or ODs using pins, you can easily see that these numerical methods in terms of accuracy and time consumption actually they dominates. So for pins the results we will get, but if you do a comparison, the time comparison with your existing numerical method, let's say you are dealing with boundary layer problem or 2D these fluid flow problems, 2D or 3D this forward problem, you can see that that result which could come in a fraction of second, the PD these pins may take a long time to find the solution. This is one drawback. And actually it also what is called this corner singularity, although it is there with numerical methods also, but in PD sometimes it means what is called approximates this corner very badly. So that become very difficult sometimes to have that for this fluid flow or convective heat transfer problem to have a result of that level of what is called these existing numerical techniques. So also you need a what is called this GPU and those things. And although at the recent time, a huge amount of what is called advancement is made for these pins. Yeah, and you can say you can see monthly huge number of papers are also coming. There are so many advancement, like so many variants of pins also available. So altogether, it is if you are using some higher dimensional problem or some ill-posed PDs, maybe parameterized PD or inverse problem, then these pins could be a very nice choice. But when you have only when you are using some existing pins, what is called framework, but your main goal is to explain the physics of some system, then I think this numerical result you can have some better approximation in terms of time and error also. Okay, so there is one example. We can see that we want to solve this. Here, actually, the solution is known to us. So the right hand side is written. So the solution will be sine of I think sine of pi x. So sine cos negative. Okay, sine of pi x. So in this case, the residual there u gamma, it is actually your network which you have computed the derivative, for which you have computed for boundary. This is the let's say the domain is 0 to 1 for the right hand side boundary. Good. So now your okay, is it not complete? Okay, so this boundary loss you will add up, then taking the residual here we will add up, and you can take the residual here and you can add up those all three together and go for optimizing the total loss. So for this, actually Navier-Stokes and those things, although there are few means little tricky this Navier-Stokes every time, or porous medium, whatever you are dealing with. So what the main problem actually lies on this pressure. So actually here the Navier-Stokes equation, that is actually, if you see its structure, that is actually based on this conservation laws. So in momentum equation, conservation of momentum, so del P, so we have a term, this pressure gradient, but this pressure which is itself is not a force, but pressure gradient, that is a force. So actually if we do compute this velocity and pressure at the same point, the velocity, the force, actually the velocity which you are computing, that actually is not experiencing any pressure gradient. So that's why in typical numerical technique, like finite element or finite volume or finite difference, we go for this grid staggering, or in case of finite difference like Mark and solution method, or finite volume, we go for this staggered grid. And finite element, you know, those this Taylor-Hood element or mini element we do take in consideration. But in this case also, those things from physics point of view, you should take care when you are solving. Although if you compute at a point, you will computer will give some number, and sometime and maybe many times it may match to the given solution, but you should also take care about the physics, not like that we have a network and we can neural network, and here we can compute the residual, we can put everything to the network and find the uh, result. So when we are actually using it, we should utilize it with care. Okay. So for verification, actually for verification, actually we should see the convergence plots maybe in a log scale, because there will be so much fluctuation, or this physics check whether it is divergent free, and yeah, if yeah, you are working with a divergent free system, or at least the boundary condition it should satisfy. And also this error matrices, you should take care, both L2 and L infinity or relative error, because this L2 you will get the overall how much error you are, but L infinity will give the worst case. So it may have that at at some single point or few number of nodal points, the network has not optimized, but overall it has a very good performance. That also happens with pins. So that's why L2 and infinity, both it is better, good practice to take care about both the errors, and also this reproducibility. And also you should also means tell about your sampling strategy, activation function, then which type of optimizer. And this is also very crucial for pins, the weighting, that is means how much weightage you are going for boundary and as a boundary condition, and how much you are going giving to this PD. Okay. And in this the next session, in our this hands-on session, we will see some implementation of some these standard basic cases for this using pins, using PyTorch, and also using DeepXD. We'll talk about little bit about DeepXD. So thank you everyone. So if you have any questions, please. Hello.
Come here. Yes, sir. Yeah.
Uh,
So we so any questions from participants? So offline participants have having the question. Yeah.
yes, please.
Sir, one question is there that we are approximating that the PD, right, through
Yes,
neural network. So that
yes,
neural network, what we get, that is one kind of function. Then
yeah,
that function is continuous or not? That is one question. And second question is that when you are taking that collocation point through that those method what you told, then how many point we should take that we can approximate properly?
okay. So if I come to your first question, so that is actually here. So your question is, so we are actually approximating a PDE.
Yes,
So
yes.
for the simple case, you can think of you are approximating an Poisson equation. Okay, let's say in 1D with Dirichlet boundary equation, boundary condition both side. So that should take the form of uxx equal to, let's say, -1, correct? So that you actually you want to find, that is actually your solution. You are trying to find that u minus, in this case u gamma or u hat, that is less than epsilon. So that will be approximate solution. So if I just can you see the slides still here? So can I actually I think I can write something here. uh, should have pencil, just give me 1 minute. Okay, yeah. So here actually the neural network, when we are actually constructing it, so first you think of, let's forget about neural network, that u star or u gamma, in this case actually we are actually using this notation, I think u gamma x, that actually you are trying to means have this approximate solutions. Let's say u gamma, you only have, you forget about neural network, that is, let's say, tan of hyperbolic of, okay, some, so what's notation we are using, w x plus b, correct? Here you have only one function. Now what will be your job? Your job will be to compute the residual of u minus u gamma. So that residual, you will try to find this best possible w and b, so that their difference, their norm become up to your desired accuracy. But here, so that's why we take this. Actually, if you see this part wx plus b, this is nothing but an affine transformation, or correct? We have one scaling when we are multiplying with w, and we have one translation, that is b. So this is continuous, then followed by a activation function. This activation function, that's why I was telling that we should take a activation function in such a way that it should have it should be continuously differentiable, or at least up to that order. You have the PD, correct? So it is actually function of function. Then actually we are summing up. See, if you have more layer, that this function, let's say that this sigma of W transpose, this is actually matrix. In this case, it will become this will take an input as to its what is called this the next layer. Then it will be input to the next layer, like that it will go. And for this number of points, it is very crucial. So far, actually, we start with some number of points, and we see the performance. Then it is also the number of points, also like an what is called hyperparameter tuning. We do keep on what is called tune for this problem, correct? Hello, is it
Yes, sir.
so overall, if I want to say that taking the number of point, it is based on your means you have to start somewhere or see the literature for the that type of problem, how many points people are taking.
Actually, sir, problem is that if we'll take like Latin hypercube sampling, we can sample anything. Means for future also we can do that Latin hypercube sampling. But which one is best, that Latin hypercube sampling or mesh-based that point? Because after that only it came. No? So.
Best, actually, it is very hard to say, but you can go with this Sobol sequence. It has low dispersion and it works nicely. This Sobol sequence, if you go, it is actually not random point, those are quasi-random number generation. But this maze-based point, those actually sometime I do use to see this side-by-side comparison with the FEM result, this Galerkian or discontinuous Galerkian, how much deviation on the same number of nodal point it is having. So you can actually give a try with both, and it is better you start with some whatever it is, this random point, and go for this adaptive sampling. That actually will increase the accuracy and also your this time this requirement. Both you will get benefited.
Okay, sir. Thank you so much.
Okay. Okay, so any
other question? Yeah, they have question. Yeah, they are very much interested. Yeah, it is good. You can take. Hello.
Hello, good morning, sir.
good morning.
I'm Madhu.
Yes, please.
Sir, my first question is, so when we are using optimizer, we'll be using Adams in first stage and in the second stage LBFGS. So I used learning rate in Adam, L is equal to 0.01, In LBFGS, I used L is equal to 0.5. I still feel L is equal to 0.5 is larger number.
Sorry, your voice is you want to tell that you so actually this Adam and LVFGS both are different type of optimizers, correct?
Yes, sir. So Adam is for the initial solution, and LBGF it will give the robust solution. It will still optimize and give convergent solution.
Yes.
Yeah. So my question is, in Adam, I used learning rate L is equal to 0.01.
0.01, okay.
Yeah, and in LBFGS, I took L is equal to 0.5.
0.5, okay.
Yeah. So actually, I feel L is equal to 0.5 is higher, but I still got solution. The main question is, if I still reduce L is equal to lesser than 0.5, do I get a better solution? Does it make any difference?
Sometimes actually this learning rate that makes difference. So in many cases, in LBFGS also, if you can go with in LBFGS also with one learning rate, so where Adam actually works with very small learning rate, but you can see fluctuations. On that case, you can just use that as initial. At that stage, if you sometime reduce the learning rate for LBFGS, you can go
Yeah,
for
sir.
a
I actually used, as you said, L is equal to 1 I took. I got very messy solution. Then I
actually those
reduced.
that maybe it is actually not converging.
Yeah,
So
yeah.
that
Yes. It was the problem. So I reduced and I got.
so in LVFGS actually it has actually like LVFGS it has means inner iteration also. So how many batching inside actually it do some like mini batching. So that there also you should change those parameters that how much uh, means how large batch you want to take at one time and how many interior loop you are taking, correct? So
Okay.
if I just want to show you uh, lbfgs so I am just showing it from PyTorch documentation. You can see yeah, whatever framework. So here actually not only have this learning rate, correct?
Yes,
We
sir.
also have this max iteration means how it does the it is the in what is called interior loop it has. Then this interior that how much tolerance it will go through, and also this history size that also these two things you can just change and see, and this search line also you can change. So with learning rate you just make a try by changing these two. By default actually it takes 20 for max iteration, interior loop, and history size 100. You can change to 550 and more number of interior loop, only one interior loop. You can just make a try and error and you can see sometimes it may work with more number of interior loop or taking this history size larger. And if you want to know about what is this history size actually, if you are using PyTorch or whatever their documentation, it will be written. So in history size, if you all the parameters they will give their description what it means. The history size is update history size means and you can see the theory for this LVFGS also. Actually it is actually BFGS, actually L it stands for this low memory. Actually here actually if we take the fully how that many sample space, your system will not have that much memory. So that's why a part of the sample point we do take. Okay.
Yes, sir. That history size
Those
means
also,
instead of taking 100, if you consider 500, so it will consider more number of points, and we might get better
yeah, it will
solution.
take little bit of time. I'm sure if you should have that sufficient number of memory, maybe in GPU or RAM, whatever, what type of computation you are doing. So not only that, every time increasing the number of point, you will have better result, or increasing the number of what is called network number of layer, you will have better result. There are some problems which, if you take only single layer or two layer, you can have efficiently very good accuracy, good result. But if you go with a very deep network, yeah, it don't give with the same framework this a very good result. This also happens with pins. There are many examples.
Okay, and in LBFGS, in tolerance grade, I tried for 10 power minus 11. So it's not necessary to be getting 10 power minus 11. We can also get 10 power minus 6 like that, no sir? Because I got 10 power minus 6, but I tried for 10 power minus 11. So it is not necessary to get 10 power minus 11, right?
No. So if you don't give anything, just give up to this, the model, if you just pass it, those it will take on its own.
Okay. And when you said about backpropagation, automatic differentiation, does that mean like we are finding local minima and adjusting the weights of the neural network? Is it right?
This differentiation, this auto grad actually, if we say what we say, actually this back propagation, correct?
Yeah.
Back propagation, it is nothing but chain rule derivative, but it works for scalar functions. But this autograd, which is actually, I told actually in terms of this PyTorch only, correct?
Yes.
So this autograd actually, it works for, it is called this vector valued function also. So actually this back propagation, that is actually a what is called the subset of this autograd. So here they have very nicely explained. It is a some graph based what is called this derivative it will found. So actually like previously, as she asked, that this neural network, if you are using pins, at one point of view you can think of that it is a function. Like if you are using you have used this finite element previously, you take some basis function, there you have unknowns, thus we find the best possible value for those, the basis function, and sum up those become element wise solution. Like that also here actually we have a function, this weights and bias, which is in terms of machine learning they do use. Those are actually what is called parameters that we optimize. So that function we have to find the derivative, that we do compute using this in this what is called PyTorch framework using AutoGrad. It is not necessarily that only AutoGrad, there have other framework also, you can find the derivative. Ultimately you have to differentiate the network to compute the loss function.
Okay, when you said about loss function for PD and boundary conditions,
Yes.
if we define that loss function directly with PD plus initial condition plus boundary conditions, then we no
Yes.
need to find separately for boundary condition loss and physics loss. Is it right, sir?
No, yeah, those you actually you can monitor. Actually, it is not clear. The question is, so we sum up the losses. Then what is you asked? Sorry.
My question, you said we need to observe when you were saying, you said we have to do separately for boundary condition loss.
For observation, actually, those losses you should observe separately. The reason is, for many cases we will see in our hands-on, only the differential, the PD that actually the network actually takes care about the PD, not about the boundary. The boundary residual, you can say that it is not even up to 10 to the power minus 1, but PD it is 10 to the power minus 3. But overall, if you see the interior, you will have more number of collocation points. So overall, you will have a good accuracy. But the physics, it does not actually meeting, because whenever we see for this numerical result, so we always take care, at least boundaries should be satisfied, the Dirichlet boundaries. at least this what we can use.
Okay. And in reproducibility, you mentioned about seed. Can you please tell about seed? Because I used 43 and I didn't get the solution. Then I went for 123.
Actually, this random point generation, whatever we do use, those are as per my knowledge, none of the technique is what is called completely random. So if you just want to see, you can the one of the basic random point generator, that is mid square method. You can see how it works. So whatever random point we use in Python or MATLAB, they use a certain algorithm, correct? So middle square random number generator, if you see here, actually you can just understand it, why this, how this seed works. Actually here the mid square works like, you give a seed, this is the seed actually, then you square it, take the middle two middle terms, and that one use as a seed, then like that, those are actually random points. So in this case, actually the repetition, and sometimes it gets stuck. So that's why mid square, it is for understanding, it is good. But in system they do use, there are many advanced methods. So that's why if you keep the seed, means for a certain type of algorithm you're using to generate random points, all, so that actually will preserve it. So like if you want to see that numpy, what algorithm it use. So it will tell, and you can see their mathematical background, that how actually it do they do take care. Okay, so that's why, or otherwise, actually for solution of a PD, this grid independency is very one of the means a key point. So whatever random point you generate, every time you should have the error fluctuation within a very means small amount. Okay.
Okay, sir. And can you say why we use normalization and regularization?
Sorry.
Why do we use normalization and regularization?
Okay, this actually this normalization, you have to do like if I want to say this what is called this regularization is required. So before, if I just talk about this regularization, correct?
Yes, sir.
So sometimes actually when you are optimizing, the solution actually may not converge to that required function, which actually we don't know for this numerical solution. But if you add up some regularization, that actually will help you to at some point, actually you may have, this is one of the reason, you may have the abrupt oscillations, correct? So those abrupt oscillations or if it is noisy, those noise you have to actually take care. So that's why this regularization is very much important, not only in the spins, so almost all numerical method also. And
Normalization?
for normalization, actually, if you keep everything, let's say in 0 to 1 or -1 to 1, so in that case, all data this collocation points choice, those things will become means what is called systematic, and there are some issue with the statistical point of view also when we are actually generating those things and doing this deep learning type of stuff. So that actually otherwise also you may have the solution, but this solution sometime it will, if it works it will work, if it don't work with that same parameter it will not work. It is better you bring everything in a you do the scaling to the input and output, or sometimes this due to this sparsity and in many cases there is a abrupt change in solution. So those things, if you want to capture and actually see the effect, so this normalization we should do.
Thank you so much, sir, for answering my question patiently. Thank you so much.
Okay, thank you. So any questions or queries or suggestions?
I think from online participants, you can ask questions. Offline, so they're asking questions.
You can write it on the chat box also. I can.
Yes, yes, that is also. Anyone from online participants, you can ask the question. Okay, sir has also, I think, hands-on means practical things. Are you going to take a few minutes break, sir?
Yeah, yeah. In 5 minutes, I will again. It will be online. So 11:50, within 11:55, I'm attending again.
Okay, fine, fine. So we are having 5 minutes break. Then we'll start it again. It is a very interesting topic, you know. Okay,
Thank
sir.
you.
Thank you. Very offline. Non.
If there is also any online session, you can connect.
Hello. Hello. Can you hear me?
Yes, sir. Yes, sir. We are here. Oh, okay, fine. So our next session is going to start. I hope it is practical, sir.
Yes, yes, hands
Practical, sir.
on.
Oh, very good. So, okay, sir. Continue. Thanks.
Yes. So, good morning to all of you once again. So, this session we will see actually some of you actually I know have started working on this, but I'm keeping it as basic as possible. So, to start with, these pins, and for this, if you also want to see this at this time, so I'm just sharing this uh, codes. You copy it in your okay, so you will not be able to edit, but you can copy in your collab, and I'm sending it in call message, the link, and just access it. Hello.
Yes, 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 sir.
Okay, so is it visible?
Just for a moment, I think.
Actually, I think I not shared it.
No,
I'm
nothing
trying to.
is showing. Just
I'm trying to share it. Just please give me a moment. I'll. Okay. Is it visible now?
no, sir, till now. Maybe it will come. Just for a minute, maybe. But it is not showing for us.
Okay, I'm sharing again then. I have to go for entire screen. I think now it is visible.
Ah, yes, yes, yes. It is beautiful. Your drive is showing. Yeah.
So there, this link I have shared in your what is called this in chat box.
Yeah, it is share.
You cannot edit there, but you can make a copy and edit this. So actually, I will go use this PyTorch
Okay.
uh, for this hands-on. So the problem actually that was this Poisson equation. Actually, this right hand side is chosen in a way so that we know the solution. That way we will able to make a fair comparison. Okay, so okay. So if I hope you are familiar with this Google Colab or at least Python. So here those are cells that those we will run one by one. But for Colab you can use uh, what is called, if you run once, it will actually connect to some runtime. So here you can see that what resource we have. If we click change runtime, so if you are using first time, you may have access to this T4 GPU or TPU, but I have exhausted the time. They will not allow me. I'm sure they will ask for money. And if it is get connected, then that is okay. We can go for okay TPU they have given. So here you can change the runtime. So actually, then we will able to use this CUDA. So the first cell, you can import them whenever required also. So we import this torch.nn, this module. From here we import, and then optimizer, that module, and those are for this visualization and those things. Those are actually handy. This NumPy, we will convert this tensor to NumPy array, and matplotlib is for plotting. So that only. This is for this all tensor related issues. Sorry, this works, and this is for this. So let's run the first cell. So the libraries will be imported. Then we can choose the device. If we want to use only CPU, if we don't use this line, you can skip this. It will by default use this CPU. Or otherwise, if you have this CUDA, that is maybe GPU or TPU, correct? So that you can seek for. If torch.CUDA is available, if this is true, then it will be CUDA. Otherwise, it will that as usual use CPU. So in this case, since we are connected to T4, so that's why it has given us the access of CUDA. But if you have in your local system, that you can use, or if you are using some MacBook, I think that is some MPS or like that. It is named. It's graphics. So this actually what is called very here actually first you can define this class, correct? This Python object oriented programming, if you know. So this network class, it is available. So this is one of the standard. Here we can also make this, you can write it if you are good in Python, you can write it in your style also. So here actually, if you see that that NN dot this NN in PyTorch, this neural network, it has the sequentially we actually this feed forward network we will use here. So we have an input. So the problem is one dimensional. So all input will go from the one dimensional co-location point. So we have one input and we have output, that is U. So one input and also have one output, correct? So here actually one hidden layer. So we are using this tan hyperbolic activation function, and it is connected to this output layer. You can increase the number of layer by writing again. So you have one more layer with these 10 neurons. So let's see the first run with let's say one neuron, and then we are telling that it is a feed forward network, and we can use a initializer, correct? All biases to 0, and this is there are type of initializer from the deep learning nodes. You can see the types of initializers. So we're running it, so it is executed. So tick marks means it is executed. Now we have to compute the loss functions. The function we are defining here, actually this model that we will pass, this is one argument, and x is the nodal point. And here the thing is for the here actually whenever we are doing some stuff of derivative, we give this required that true, means we will compute the gradient. So that is not necessarily you should every time give in this way. When you are generating the random points, there also you can give, if it supports that one argument, that we use the gradients. So U, that is the approximate solution, will read the model, that is the neural network. Then UX we are computing. This is also PyTorch's standard, means what is called syntax. Autograd you are using will differentiate with respect to X and create graph true, and it is the component, the first component. You can just see their documentation for better insight. And again, if we differentiate this UX, then we will have UX6. That is again like this we have computed. Actually, here actually we are taking this AutoGrad, which is actually this library is there with Python, Python PyTorch. Now this residual, this is the right hand side, correct? But here this pi square, but here you should take care about this, otherwise you may encounter some error. This pi, it is of this from the torch, and not from numpy. If you are using, then sometime some version it will show some error, because all tensor will added up with tensor, and like that it will keep on going. And this is our residual. And on boundary, on the left we don't need any what is called derivative. And to device, here it is we are using that, otherwise it actually initially those are calculated in CPU. Now if we are using GPU, that will send to GPU memory. Then you left and you right, you are actually computing those are those what is called these residuals, boundary residuals. And for this, even you can give mean square here also, that L2 norm, no, not here, where it was here, in the return you can give the mean and torch dot mean, and it's got that residual. I think for this code it is this norm is calculated after means computing the function. Okay. Now epoch is that epoch actually that means the number one, all means when we say epoch, when all weights and biases are updated and you have gone through all weights and biases, that is one epoch. So that means it is kind of loop. So we will go up to 5,000 loops, and WT here it is actually this balance. Okay, so here actually this torch mean, then we are calling this PD loss function. So that part actually I think better to keep it there. So if you want to keep it there, just cut it. Okay, so we'll just now actually we are using only Adam optimizer. So we are telling that this model actually now this is nothing but this PINN. Actually it is, you can use your name also, that is the class we are defining, that name, that neural network, that is actually here this model we are telling, and we are passing it to the GPU, since we are using here GPU, and we are using a optimizer, this Adam, with some learning rate. This learning rate is also an hyperparameter. Now for initial point, I'm using simply this rand from this torch. It will generate random points. Or if you are going for this Sobol sequence and those things, that you can go with, and you can even you can use this some other, or you can write your own code to generate random point. Now in this loop we will actually do the training. So in this range of epoch, the optimizer, what is called, it will actually take this loss and this loss function. You please go through this PyTorch documentation. What is backward step? Those are clearly mentioned. So this actually framework that goes. So now we want to, you can print as many as you want. Here we can print the losses and we can see how the training. So you can see the loss is decreasing. So it is simple problem. It will go up to, I think, 10 to the minus 4, 6. It should go with Adam only. Okay. So this is the print string. We are printing only total loss. We can also see how much PD loss and boundary loss also. So that I will see. Now this is to compare. Since for this case we know the analytical solution. So for an analytical solution, you take some numbers because computer will work on these discrete points. So here again for the same point, actually we are converting to what is called tensor, and we are actually doing the evaluate this model on that point. And if we see the plot, this here this it is actually what is called very much we have very good 10 to the power 6 into 10 to the power minus 4 residual. If you go for some more loops, the error may reduce somewhat. Here, so this is a very basic. So you can increase the number of it is called this layer here. So previously have single layer. Now, so if we give the run all, let's see, we have increased the number of layer, but in this case the error is okay. Sometimes it has a very this fluctuating nature will be there. After that also, is it okay? So I think it is very simple. There is not much difficulty. So I'm disconnecting this runtime. Yes, if they allow. Okay. Let's say for heat equation. So it is also the same 1D advection diffusion equation, and just this is only heat equation. So let's say okay, before going to 2D, one dimensional problem, one more. This one dimensional advection diffusion problem. So in this case, at least they should give TPU access, otherwise I cannot show you any convergence. Okay, it is T4. So this is steady state advection diffusion equation. You know about this advection term, diffusion term. So when problem arises, when this P is what happened? So when it is advection dominated, so when it is diffusion dominated, we know the problems for numerical point of view, it remains easy. So again, we seek for whether we have CUDA or not. Then you define the neural network. Let's say here also we start with one hidden layer with 10 neurons. And like previous, we have computed. Then the losses we will compute. Okay, so P times this. So here also this that structure is mean. So whenever we have this torch.mean, actually it goes for a back propagation. Okay, no issue. The learning rate we have said something. So where is P? P is 0.5. So that means if P is 0.5, so 1 by P is large. So we have actually diffusion dominated case, we can say. In that case, you see the result and training point we are taking 50. Here also when the problem will arise if we just see if it is diffusion dominated directly it is up to 10 to the power minus 5 6 it is reaching very efficiently without having any difficulty. You just try this with P, let's say 10. Try once with P10 and see what happens. Here, see in this case, the result is approximation and pin. Those are very good, but let's change it to P equal to, let's say, 1. So we have mixed. One, it is running with that. See, the loss is. So, what are our boundary conditions? Okay, see, it starts deviating. In those cases, actually, we need to tune it. So that's why this hyperparameter actually it is in your hand. Let's increase further. Let's say 5. See, now the error is no longer means what is called decreasing like previous. So here also you see the result now it is deviating and see about the boundaries. The boundary are not met. So in this case, if we want to print, it is total loss, or we can also print PD loss. Here it is OD. So OD. And also,
Hello, sir.
yes,
Actually, I have one question. Can I ask you?
yes, please.
Actually, we are also working in this field only, so we don't have exact solution. So in your code, you said that the analytical solution. Can you drag upside?
Yeah, I know because here for tutorial point of view, actually we are
You have
actually
mentioned already your exact solution. Actually, we are working. We don't have exact solution.
yeah,
So
I,
if we are
I got
doing the pins, so actually we don't know that whatever we are doing that is the correct or wrong. So I have a question that so whatever we are doing now. So how can we check that we are doing the correct or wrong? So here you are having the exact solution. From exact solution you are comparing pins, correct? From there
yes.
your graph is visible. For we are working, we don't have exact solution. So how can we compare that? Like how can we know that we are doing that is correct or wrong?
So exactly you are working in which field?
That is in fluid dynamic only.
Fluid dynamics.
Yes, have the
Okay.
equations, boundary conditions and initial conditions also I have, but we don't have the solution for that.
Okay. So actually, the main
Yes,
reason
actually we don't have the analytical solution for that. We didn't
I,
calculate that.
I got
Like
it.
we are doing for just for a random example, we did in Mathematica we calculate the one of the solution just for the practice purpose. But now we have a problem. But in that problem we don't have any analytical solution. So how can we find that, and how can we check what we are doing that is correct or wrong?
I will come to that point. Just
Sir, like in short, my question is that we
yeah,
don't
I got
have.
it. I got it. I will try to give you the insight how people actually do take care about this. So why I was telling this. So in this case, I will get back to you. So that is also you can see the click here. See if we monitor here. So previous we have monitored this, correct? So if we monitor here, we can see that on boundary, the network is not trained. It's not getting trained well, correct? The solution in each run because it may get deviated. But for a numerical sorry approximation solution, so let's say just increase the weightage towards this boundary, this boundary loss. So here it was added up, here it is added up. So again, if we restart and run it, we have only single layer, so that what is called accuracy may be increased by increasing this number of points here, or number of hidden layer, that making the function go here. In this case, you see whenever we have given some weightage to our boundary, the boundary is getting learned, correct, up to 10 to the power minus 4. In this case, you will see the result actually, see. So at least these boundaries, that's why we do take care about, we should take care carefully about these boundaries. So until your boundary are satisfied, the interior actually, interior also, that the error that get more improved than whenever we have another what is called this voltage. So in your case also, so whatever problem you are doing with pins or any other numerical method, first you see the boundaries. If you have boundaries, so if you have at least you should have some Dirichlet boundary condition, at least one. So you have some Dirichlet boundary conditions. I hope those problems should be coupled. So in coupled also, if all are means Neumann, then the problem you have to see that theoretically whether it is the solution is stable or not. So at least one Dirichlet boundary condition you should have. That boundary condition first you check. Then the second, what you can go for, you can take some reference solution using known numerical method, like if you are working in boundary layer, this shooting method or some other technique you should go with, or some if you are in or this 2D, you can use some FEM reference solution, correct? And those you should keep in reference. If since until you have a strong theoretical means background for this um, for the problem which on which you are using the pins, because for finite element or finite difference we have those error bounds we know previously. The stabilizer, those are well established, like if you can see. But for pins, those work actually, people are working as I started. But if you are using for this research work, some validation part you should take in consideration in terms of some numerical result or analytical result. Or you can see also that the boundary loss also, whether it is at least this boundary is satisfied, boundaries are satisfied or not. It may happen that only boundaries are satisfied, the interior loss is not reducing. That is also indicating that it is not well trained. Both should be, and boundary, you can expect a better accuracy on boundary than your interior, correct? So if you, for the same problem, let's see by increasing one more layer with having this same penalty term. So now can we just check with one? So I'm restarting it so that all parameters should start from the beginning. Otherwise, what will happen? The previously some parameter those are trained already, that will actually come in picture. So here some error we have obtained. Okay, so the issue is here we have 10. This should, we should make 20, or this should also 10. We should keep it. Okay, increasing, see this number of one layer, if we increased, we have increased, then also it may work that it is getting trained, but it is up to you where you want to put more effort. Since we are increasing this number of layer here, we are actually having more computational cost. So here also increasing this number of point, or maybe it may work for you increasing number of points also, correct? So let's see one two-dimensional example. So here I can disconnect it. Okay, we are trying to solve this with zero Dirichlet condition. We are solving this Poisson equation. Here we import this like previous. So actually I will try to change the runtime. Just please give me a minute. How much time left out? Okay, now I think we are connected to, okay, we have access of CUDA. So here we have two hidden layers. So here we have input of two-dimensional because we will take xy. So in 2D we are solving x coordinate, y coordinate, and we have only one PD. So we have one output, that is solution that we have now. Here actually now we will calculate the gradient separately, ux, uy. So we will take help of this torch autograd, and after doing this autograd we will have two components. So actually those are some arrays ultimately, and not array, these tensors. So from the tensor we take this component from 0 to 1, this component as ux, and the second it will be column this component wise, that is uy. So again you take the derivative for this ux and uy. Now you have your loss function, this fx, and you have your loss function, and on boundary all are 0. So here you can just give -0, and if you don't give, then also it is actually, it will treat as 0. So for visibility you can just give here 0 square, correct? Then your loss function, that is it's called this model we are sending to GPU. We are setting our this optimizer. Now we have to generate some interior collocation point and some point on boundary. So inside the domain I am taking 500, and on boundary 200 points. So boundary point you can go for random. I am using a linspace. So each boundary it will get 50 points. So then again we combine together all the points, interior and boundary, because all together it will go for training. Correct? So we can just have a visualization. So that's why we don't use this this random point. That's why this some other type of what happened. Actually, this random point it actually get clustered in many places. So there are some better algorithm which actually will have low dispersion. Correct? So we can just increase some more points there inside the domain. It's 1,000 points. Now it is little bit dense. So yeah, even though this only random this algorithm which is with this tensor, it is not that much recommended to use because of this clustering. You use some other better type of which will have can give you a good result. So here also it goes that like that, but only one thing, on the boundary nodes we have to separate, and the interior collocation point we have to separate them. So during training we are passing all xy train. So xy train actually it okay, here it is, this xy train and this boundary xy boundary, and for boundary loss we are sending this nodes, and it is calculating its whatever called, that is uh, the loss it will compute. So this Poisson equation, it is this I have parabolic type of, no sorry, elliptic type of problem. Those are, for those you will get good result rather than, so here you see that it is oscillating. So in that case you we have to go for this hyperparameter what is called the result may not be as you we are expecting. So they see at least these boundaries are also not. So can we just means increase the weightage to boundary and have this, or otherwise we have to increase the collocation point or number of layers or number of neuron. So those all falls under this hyperparameter tuning. Okay, let's see. Or in this case we can think of decreasing the learning rate also, because this oscillation, if it so we have little better. So one more time, can we go? So with where we have set the learning rate, or we can just increase the one more layer you can add up, or here let's say you go for 20 20.
Sir, you are using here 10 at activation function, right?
Yes.
That in that in your class you told that we are searching this activation function from grid search or something. So can you show that code, that how can we do that grid search method and doing this, and
Correct.
collocation point also select
Sorry, this activation function, we will actually use those which are actually, since we are using this PyTorch, what is called library, whatever they have among them we can choose. Okay, we cannot go beyond, otherwise you have to write your code.
No, no, sir. Actually, you told no for activation function. If we want to select means it should be means if we select double derivative, it should be that activation should be double derivative. Here also you took double means second order differential partial differential equation. So we'll check 10h. But why we can't select anything else? And for that I did not understand.
Okay, if you see this derivative of 10hx, how much it is? X square, correct? So again, if you do differentiation to this, you will have other differentiation. But let's say we are using, let's say, ReLU. Just see how this ReLU seems like. You, instead of this, if you want to see the ReLU is continuous, but here it is not differentiable. Even first order differentiable you will not have. So here, if you want to see, the reason was the reason I told was that to find the derivative, now to find the loss function, we have to compute the derivative of the network. The network is nothing but function of your activation functions and their combinations. So that should have derivative. The tan H also have, so you can use sigmoid in this case, because sigmoid, it is continuous, it is differentiable. But ReLU, or what is called this uh, this one this lucky ReLU, those you cannot use, because here you see those are continuous but not differentiable, correct? This was the idea which I told. Or some other activation function, if you have, you can use it based on here actually 10h. One difficulty for 10h is, okay, and one more thing, that you should not use those activation function. There are some activation function for which the first derivative is, let's say, constant. The vanishing derivative also you should take care. Means after some iteration, the derivative may get vanished. Means all are zero. Correct? That type of. So here also for ReLU, if you somehow, if you take the what is called this x, so if you make it continuous somehow, and if you take the second derivative, so it will be zero every time. All derivatives will be zero. So all that information about physics will get lost. Correct? So two things. One, it should be differentiable continuously and without having vanishing derivative. So here it is actually diverging using the number of what is called layers. No, sorry, number of neurons. So better what we can try to do. Okay, we have a very large learning rate. We just reduce the learning rate little bit, and let's see. So how this gradient descent those works? Now see it is converging smoothly, although it may oscillate this, but has better trend to have a convergent result. Okay, you see that result. I think one more time we can see this to at least triple 10 to the power minus 3 or 4 order. It is oscillating and reducing, no issue. This is a common phenomenon. Okay, so like that, you have to take care about this. That was lambda b in this case of there. Then epoch is nothing but how many time you are updating all weights and bias. Second is number of layer, their weights and depth and height, and then this crucial this learning rate. Okay, is it working somewhere? That actually these codes may not be directly applicable to your now it's you see it has, but these corners you can see there the convergence is very difficult, so that's why these corners to take care about the corners you see almost close to each other, but this only close to the boundary it is oscillating. If you want to see this, what we can do, u exact where is u pin, here we have u pin na? Uh, uh, in-
Sir, another 2-3 minutes.
okay, sir. No issue. I will just complete it. Okay, so you say close to the boundary, this is zero, how it is training. So it has some negative, positive, like that. So this happens with this L2 norm close to the boundary. If you want to see this site, you can just see. So there you have zero. So it has peak here 10 to the power minus 8. But overall, the error it is close to zero. That's what actually this close to the boundary you see it is actually deviating from zero largely. Here also if you see another boundary also you can see this. So I can complete this hands-on by showing this. So in this framework, if you are using PyTorch, we have to write many things like defining this thing, that thing, this computing gradient, everything. So there is a very good library that is deepxd that you can use. So here with an example I'm showing you, it is not installed in our so first we will install this deepxd, correct? So if you just give 1-2 minutes, I just want to complete this because it is uh, 44. Okay, so then you can call this deepxd. Now here actually we define all the functions. Here actually we don't use this autograd. We compute the Hessian. That's why it is more efficient. And we also use this Jacobian for first derivative, and for second derivative we compute the Hessian. From Hessian we compute. So Hessian will have coordinates. From the coordinates we compute. So here we have only one scalar problem. So that's why we no need to give the coordinate. Otherwise, if we give the coordinate, that will compute that second derivative at that point. If we need the first derivative, we compute the Jacobian, and it has the matrix location 0, 0, 0, 1, 1, 0, 1, 1. So it is the exact solution for this case. Now here this is inside the library of this deepxd. Here you give the domain, then the boundary Dirichlet boundary condition, where are Dirichlet boundary condition, where are Newman boundary conditions. So for Newman boundary condition we are calling this as an operator where it is this Jacobian we have computed, yes, Newman in operator form. So there we have computed this because we have one Newman condition, ux du dx equal to 4 at one, and another side Dirichlet. Now, if you compute, then here to make the network, we just have to write one line, one input, the first layer will have one neuron, then we have three hidden layer, each having 50 neurons, and we have one output. That's all. It will actually, in backend, it will construct. And activation function, we are using this can h. And for initialization, it is using this Glarut normal, which actually we have written a part of code here to initialize this. So that part actually we are just telling that you do the initialization. Now we are making the network. It is feed forward network, layer size, what is activation function, what is initializer. Our job is done. Now we are telling to train it, and it will compile using this Adam. It will have learning rate this, and the matrices actually, that actually L2 norm it will calculate, and we can also save the history and number of iteration, the training history. So now it is actually compiling. Now it start training the network. You can see this loss functions that is going on. So if you are only have some problem, you can try this deep XD. It is way more efficient, and it works very nicely. So with this, uh, um, stopping here. So here you see, and also the graphs, this train loss, test loss, and with how it is put into the -5, since the problem we have chosen as per our. So for deep XD, you can see their website. They have well documented website. So thank you.
Okay, thank you. So, questions from online participants? Online participants, do you have any questions? Because in between we have received questions from offline participants. Now, online participants, do you have any questions? So, another thing, if you, because as per my knowledge in the current research, this is one of the hot topics I can say. So,
Yes.
that's why I think participants also they have enjoyed this session, these two sessions, and I also really appreciate to Dr. Burman for your valuable talk and your time. So okay, so and for the participants online and offline, if you have more questions and doubts, you can touch with Dr. Burman through
Yeah,
his email and all.
I
Right,
will
sir?
at the if I am sending my email, if you need some help, which is actually may have solution to me, I will definitely try to clarify, because this field we are all actually something learning and something working. Those are recent fields. So, and even if you want to work in collaboration, also it is open. We can work in collaboration. I'm sending my mail, and
Yeah,
sir also.
all of you, online and offline participants, you can note down this. It is
So
Probir at the rate
dot
IIITM.ac.in.
and thank you all of you, and to sir for giving me this opportunity, and to have this interaction with this participants also. Thank you once again.
Okay, thank you once again, sir. Thank you so much. Okay, thank you. For online participants, yeah, you know, as per our schedule, so we have lunch break up to 1:45. Again, so we hope we'll meet at 1:45 sharply. Thank you all.